Consider the gravitational force between a satellite of mass ms and the Earth of mass me. Let the radius of the Earth be re, and let the satellite be at a distance r from the center of the Earth. Obviously, the distance of the satellite is greater than the radius of the Earth. So write down the force between the satellite and the Earth, both the magnitude and direction, and how does the gravitational force change if the satellite's mass is doubled and if the distance is doubled. B. Consider the case where the satellite is a synchronous satellite, such that a satellite goes around the Earth once every 24 hours, so that its position appears stationary with respect to a ground station. What is the distance of the satellite from the center of the Earth? So here we have the Earth and we have the satellite. And so the common gravitational equation for objects outside of the Earth's atmosphere is the force between them is negative g times the first mass times the second mass over the radius squared. And so the force in this particular case would be negative g times the mass of the Earth times the mass of the satellite over r squared. And if you're wondering what g is the gravitational constant, and that is simply equal to 6.67 times 10 to the negative 11. But that's not needed for this problem. So anyway, the force, this is the force, negative g times the mass of the Earth times the mass of satellite over r squared. So if we double the mass of the satellite, we are also doubling the force. That's straightforward enough. But if we double the radius, so we make this 2r squared, then we are actually making the force a quarter of what it was before. So this would be F over 4, because 2 squared is 4. So in the case of 2me, the force becomes, 2ms, the force becomes 2f. And in the case of 2r, the force becomes F over 4. Alright, next, consider the case where the satellite is a synchronous satellite such that it takes 24 hours to orbit the Earth, so that when we look at it from the space station, it's not moving at all. What would the distance of the satellite have to be for this scenario to be possible? So we know that in order for the satellite to travel 2 pi radians, which is the distance around the Earth, it will take 1 day, which is 86,400 seconds. So omega, which is in radians per second, is equal to 2 pi over 86,400. So now, we have to find the centripetal acceleration, because from that we can get the radius. So let us write the equation of force down. So the force between these two is negative g times the mass of the Earth times the mass of the satellite over r squared. And this could also be written as the mass of the satellite times the acceleration. And so the acceleration has to be this value right here. But another way to represent the acceleration is negative omega squared r. And we found this in this video right here. So negative omega squared r is negative 2 pi squared over 86,400 squared times r. And so we can plug this right in here. And so our final equation, or not our final equation, our next equation would look like this. ms times negative g me over r squared equals ms times negative 4 pi squared over 86,400 400 squared times r. And we can cancel out the ms, and we can cancel out the negatives. And now we simply solve for r. So r cubed equals g times me times 86,400 squared over 4 pi squared. And we simply take the cube root. R is equal to the cube root g times me times 86,400 squared over 4 pi squared.